We'll move to our second talk by Michael Dine from Santa Cruz.
First, again, I would like to thank the organizers. This has been a lot of very interesting for me this morning. I'm already leaving this with a number of questions I want to think about from the talks we've heard. And I'm going to describe some work with 4 students at Santa Cruz: Jamie Law Smith, Shizhan Sun, Yan Yu, and Duncan Wood. And what we're asking about the question of the obstacles to constructing de Sitter space in string theory, and sort of backing away a little bit from the Swampland conjecture itself. And I'll explain in what sense I mean that. And I should say, first, I'm very intrigued and sympathetic to the Swampland idea, but I think one should think a little bit about this de Sitter space conjecture. So let me just make sure yeah, here we go. So, and I'd sort of like to back up and sort of remind people, including myself, that while string theory has provided tools to think about many questions in quantum gravity, cosmologies resembling our own have remained inaccessible to controlled approximations in the theory. And here I mean not just de Sitter, I mean even just something that looks like an FRW emerging from a Big Bang. So conceivably, the observed Big Bang is not described by a quantum theory of gravity or requires some still larger structure. For example, maybe within a landscape picture or something, we'll understand how what replaces the singularity. But it's also possible that this simply represents a failure of our present collection of theoretical tools. Okay. Now, of course, also as this underlying a lot of what we're concerned about here, our universe appears to have entered a stage of exponential expansion, well described as a de Sitter solution of Einstein's equations, or seemingly well described in that way. And at a time shortly after the Big Bang, we have good reason to think that the universe also went through a period of exponential expansion. So de Sitter space, in some sense, seems likely to play an important role in our understanding of our present and past universe. The inflationary period lasted only for a brief moment, and our limited understanding of how de Sitter space might arise in string theory, as if it does ever arise, would suggest that even our present de Sitter universe is metastable. Okay. And finally, the notion of a cosmic landscape introduces another role for spaces of positive cosmological constant. In particular, such a landscape might allow realization of the anthropic selection of the cosmological constant, sort of, again, this Sushi's elephant, but would seem to require the existence of a vast set of metastable de Sitter positive CC vacua. Oops. Okay. Now, the Swampland conjecture arises because it has proven difficult to find explicit constructions of metastable de Sitter space in string theory. Okay. And so I say this leads to this conjecture that perhaps de Sitter space does not arise in string theory, and then it has refinements in terms of, say, some bounds on the potential and its derivative. But backing up, well, I should say that if true, this has the dramatic implications. But rather than address the implications here, I'd like to look at the starting point. So the starting point is really looking at this difficulty and saying maybe the difficulty represents something fundamental. Okay, so one should first ask, I think, what would it mean to construct de Sitter space in string theory? And there are people on this at this meeting who are more expert at some of these questions than me, but I'm going to struggle to kind of figure out what that would mean. So in most constructions, most efforts to construct such a space, one starts with some classical solutions of the equation, say some critical string theory, some compact space and something else. And these solutions invariably have moduli or pseudomoduli. And then one adds features such as fluxes, branes, and orientifold planes, which give rise to a potential for these moduli, and then looks for a minimum with positive four-dimensional cosmological constant. Okay. And these attempts generally raise two questions. First, what's the approximation scheme? So I'm going to sort of take the point of view that if you don't have a controlled approximation, then it's not, what you're doing isn't all, I don't really want to say it quite like this, but roughly speaking, what you're doing isn't all that interesting, or at least it's hard to make any kind of definitive statement. And second, in a sense that I'm going to describe, any would-be, any would-be de Sitter space found in this way is at best metastable. Invariably, there is a lower energy density in asymptotic regions of the original moduli space. So quantum mechanically, this purported de Sitter space isn't eternal. It has some kind of history. It will decay in the future and must have been created by some mechanism in the past. Okay, and the quantum mechanics of this process is challenging to pin down. Okay. So in this talk, I'm going to actually argue that classically the notion of an eternal de Sitter space in string theory is problematic, that small perturbations near the de Sitter stationary point of the effective action evolve to singular cosmologies. And in the hopes that I can get this to work, just a picture that will I'll have in the back of my mind throughout all of this is, and I apologize, let's, there we go, is this one. Oops. So we have a potential, a field phi with some potential. The potential we're imagining has some de Sitter minimum, but characteristically, at least in string theory and string constructions, okay, there's some asymptotic region of the field space where this potential tends to zero. It might do this in some more complicated way. I'm just indicating one sense here. Okay, but we have the issues that that this state, if we somehow got here, this can decay. Okay, and the history, the cosmic history of this sort of system is potentially problematic. So let me see if I can get back to my slides. Okay, good. All right. So just to summarize, there are these two challenges. One requires some kind of small parameter to allow a controlled approximation to finding stationary points in the effective action. And here one runs into the long-standing problem that without introducing additional fixed parameters, so parameters not determined by moduli, would be stationary points of the potential lie at strong coupling. And typically attacks on this problem and the question of finding de Sitter space exploit large fluxes. I don't know I'll have time, but I may discuss KTLT later, which is slightly different. And if there's to be a systematic approximation, it is necessary that the string coupling be small and compactification radii large at any would-be stationary point found in this way. So if the strategy is to obtain inverse couplings and radii scaled by some powers of fluxes, it's also important that these fluxes can be taken arbitrarily large. Okay, now whether that's really possible is a serious question, but even allowing for this possibility, we'll see that it's quite challenging to realize arbitrarily weak string coupling and large radius with positive or negative cosmological constant. And this point has been noted also in the recent past by Jungens, Russ, and others. Oops. And the second issue, which we'll talk about, is that if one does find such a stationary point, one must ask about stability. And this is actually beyond the requirement that the quadratic fluctuation operator have a positive definite spectrum. De Sitter spaces, I'll try and argue, introduces some new elements into this question of stability. We'll see basically in terms of that picture I drew that you have the possibility of small perturbations sending you over that barrier into a region where the system then undergoes gravitational collapse. Okay, so in string theory, if we think about critical string theory, sort of what we do in textbooks, we're used to searching for suitable background geometries and field configurations by requiring that the evolution of the, by the evolution of excitations around these configurations is described by a unitary S matrix. Okay, classically, at least in flat space, this is the statement that if we have any initial perturbation, that any initial perturbation evolves to some final perturbation in some sensible way. Okay, and we'll see again that this requirement is problematic for any would-be classical de Sitter's stationary point in such a theory, say even if all the eigenvalues of the mass squared matrix are positive. Okay, large classes of small perturbations evolve to singular geometries. Okay, so overall then, we're going to argue today that I'm going to argue today that we lack theoretical methods to address in any systematic fashion the problem of constructing de Sitter space and string theory, much as we lack the tools to understand Big Bang or Big Crunch singularities in any controlled approximation. And so I'm going to claim that the existence of metastable de Sitter states may or may not be plausible, but it's a matter of speculation. The failure to find such states in any controlled analysis appears, at least at present, to be inevitable. So let me talk a little bit first about this problem of searching for stationary points of some effective action. And I'm going to be following various works for people like Andreou and Ross. After introducing branes and fluxes, one typically searches for particular stationary points of the action with positive cosmological constant, and then asks whether the string coupling is small and the compactification radii large at these points. Now, even if one succeeds in finding such particular solutions, this by itself does not address the question of whether there is a systematic approximation. The system with, so for example, if you find a numerically small value of some of the couplings, the system with branes and fluxes is not a small perturbation of the system without, and the range of validity of the expansion is one is not related in an obvious way to that of another. So if there's to be a systematic approximation of any sort, one really requires a sequence of such stationary points as one increases the flux numbers. The would-be small parameters are then the inverse of some large flux numbers, okay? And for this discussion, then I'm going to assume that it makes sense to take such numbers arbitrarily large. So the goal then is to find stationary points of the action where the string coupling is small, all the compactification radii are large, and the cosmological constant is small and positive. Oops. Okay. So I'm going to follow Andreou, for example, and study type 2 theories in the presence of an OP plane with some background metric. The first coordinates here are the 4-dimensional background, which we're hoping to be de Sitter, and then we have some reference metric in the compact dimensions, in 6 compact dimensions, scaled by some parameter rho or some modulus rho. Okay. And we're also going to include various fluxes. I'm going to include NS-NS3 forms and RRQ forms, HIJK and FQ. Okay, and I'm going to focus on 2 moduli basically for illustrative purposes. This rho and something we'll call tau, or some following these authors I'll call tau, which is rho to the 3/2 e to the -5, where phi is the string dilaton, the thing that controls the 10-dimensional coupling. And one can work out an action. The action involves the 6-dimensional curvature, the curvature in the complex space. It involves the 3-form flux squared. It involves the tension of the orientable plane. And it involves the various RR fluxes, which I've indicated here, with various powers of these moduli. Okay. And if I just think of these fluxes as some fixed integers n, so these will integers times some pure numbers, fi is some ni, and h3 is n3, we can illustrate the issues by taking the case that f4, this 4-form flux, is much larger than the 2-form flux, much larger than the 3-form flux. Okay, and then for some range of p for this OP plane, one can find a minimum. And I don't want to dwell on this too much here, just to say that, in fact, for this range, one finds that rho is large but negative, which is, of course, not acceptable. But even if rho had been positive, we would have had that the gauge coupling g squared, which is rho cubed over tau squared. You have to sort of remember these definitions of this parameter, of this field modulus tau, that this thing would go like n4 over n2 cubed. And the string coupling, as a result, would not have been weak. Okay, so just to say that there are various problems you run into here. We run into this, we don't really have a sensible minimum in this case. And even if we did, or we sort of close our eyes to that, it's not simple to get a weak coupling. Both this coupling and the radii we require to be large. Okay, the radius is large in this case. Okay. Now, in other cases, one finds other pathologies, ADS space rather than DS stationary points, instabilities, and searches involving broader sets of moduli seem to allow at best a few isolated, really, points of parameter space where such solutions might exist. Whether these might exhibit a sensible perturbation expansion is currently an open question. Whether, sort of one sometimes sort of hopes that the perturbation about this theory without the fluxes is somehow similar and the criteria for a valid expansion are somehow satisfied, but one doesn't really know that. Oops. Okay. So, so I now want to turn to the sort of cosmological question. String theory has many dramatic successes in understanding issues in quantum gravity, but as I've said before, one is its inability to describe a big bang or big crunch singularity. For example, for that picture I drew before, where the potential falls to zero, if one starts the system in the far past with expanding boundary conditions, then further in the past there is a Big Bang singularity. And if one starts with contracting boundary conditions, there is a big crunch. So just for a moment, shifting back to this picture, all I'm saying here is that if I start the system on this side of the barrier, going up the hill with expanding boundary conditions, then in the past, then the system looks like it might be a weak like maybe a weakly coupled system, and maybe it doesn't go too far up the hill. So you might hope that you have some control over the system, but in fact, in the far past, you have a Big Bang singularity. If you start with contracting boundary conditions and weak coupling, then again, you might hope that things were okay, but in fact, in the future, you encounter a big crunch singularity, and your various approximations, the various approximations you might be using here break down. So, okay. So, yeah, so here is again, I'm sorry, I have this picture here. Okay. So the question we might, what you're asking is, are things better if we start in the metastable minimum? If we somehow start the system over here, okay, are things okay? And I try to frame it this way to make you sort of prejudice you to say, well, why would you expect that there would be much better? Certainly if we just start the system over here at the minimum, it can stay there forever. But I'm worried about, now suppose I start it, but with I give it a little kick. And I'm worried about whether the system may pass over the barrier, even with a small kick, and lead to a singularity. Okay. So just sort of to remind you a little bit myself, a little bit of de Sitter space. De Sitter space can be presented in various ways. One is the following. Okay, this has the virtue that this choice of coordinates covers the whole space. Okay, and a homogeneous scalar in this space, phi of tau, obeys an equation phi double dot plus 3h sinh h tau over cosh h tau phi dot plus b prime of phi equals 0. Okay, and just to stress about this, then for large tau, okay, this field, depending on the sign of tau, okay, this term either acts as damping or amplification. Okay, so depending on large positive tau or large negative tau, we have different behaviors of this system. And let's consider first the case where we have a potential for phi which rather than looking like this metastable potential grows in all directions. So what we might have thought of as a kind of normal field theory. Okay, and in that case, in the far future, okay, the system, let's see if I can get back to my picture. Okay, so in that case, now my potential rises like this, and in the far past, the field grows, and in the far future, it damps out. So the system can start near its minimum, can start rather, the system in the far past rather goes to the minimum, and the system in the far future settles into the minimum. So we have sort of perfectly sensible behavior of the system here. Okay. The issue with this, so again, getting back to my picture, the issue here, in this case, is that if in the far past I give the system a little kick, it's amplified, and if I don't wait long enough, I will pass over the top here. So that's kind of what we're worried about. So, all right. So, go on. Okay. So for a potential that is a local minimum with positive energy density falls to zero, as I say, we might expect it would create a small localized perturbation at some time r0 tau 0. This perturbation will damp out at tau 0 much greater than 0. But if tau 0 is much less than 0, so that damping term is an amplification term, the perturbation will grow, possibly crossing over the barrier. Okay, and in this case, the emergent universe on the other side is contracting, and we might expect the system to run off towards phi equals infinity until the universe undergoes gravitational collapse. How are we doing here? Yeah. Okay. All right. So, so we're interested in disturbances which lead to motion over a barrier rather than tunneling. Okay, we might expect, however, that once the system passes over the barrier, its subsequent evolution is not particularly sensitive to whether it passed over the barrier or tunneled through it. Okay, and the reason I'm saying all that is because what I'd like to use is I'd like to use the equations that are used for tunneling of the critical bubble, the equations of Coleman and DeLucia, which John March Russell referred to. And the argument that we can use that is in either case, once the bubble becomes relativistic, its energy grows like T cubed, dwarfing any difference between whether I started out near the on one side of the barrier or the other. So right, so I'm going to skip ahead and just draw a couple pictures here again. So so looking at this picture again, what I'm sort of imagining is I start the system now over here somewhere, and I give it a little kick so that it runs over the. Oops, let's see if I can do this a little better. So that it runs over the top. Okay, and I'm going to draw a picture in a moment where I think about initial bubbles of various sizes. Okay, so bubble of radius r. Okay, and I'm going to actually draw a picture for V of r. Okay, and that's going to look something like this. Okay, so I want to talk about that picture a moment. This is a picture. So I want to think about either tunneling in this picture, where I tunnel out through here, or alternatively giving the system a little kick where it goes over the top. Okay, so those are the two pictures that I'm going to talk about. Okay, and so one can actually derive a potential for this radius r. Okay, so for example, for a thin wall bubble, I can work out the potential for r, and that turns out to have a piece versus a kinetic term, which is not quite canonical. It involves r dot squared and r squared. Okay, and there's a potential which involves r squared and r cubed. So that's this growth and fall off that I described. Okay, I think in the interest of time, I'm not going to go through the details, but just to say that you can study the system numerically. You can see that, in fact, the bubble actually does grow as predicted by this picture. And it does quickly become like the critical bubble. Once it's on the other side, okay, once you pass over to the other side, the bubble behaves very much like the critical bubble. Okay, so, all right. So given that it behaves like the critical bubble, eventually we can study the behavior of the critical bubble, the bubble that Coleman and DeLucia study, okay, the bubble that appears in the tunneling problem, okay? And I just have kind of written the equations which Coleman and DeLucia write, okay? And just to say that one can solve them. Now, for the typical potentials you write in string theory fall exponentially in terms of a canonical field. Okay, and so you might expect that the potential is not particularly important, and you can solve those equations, these equations of Coleman and DeLucia, for the scale factor. So rho is now, I should say, the scale factor. It's not that modulus that appeared earlier. you can solve for the scale factor in terms of tau. Tau is this invariant parameter that appears in the equations, and you find that rho goes like tau minus tau naught to the 1/3. Okay, but rho and this corresponds, I should say, to curvature rho dot over rho, which is diverging as tau goes to some point tau naught. Okay, and phi dot itself goes like rho dot over rho, so phi dot diverges. So both these objects become singular. Okay, yeah, so I've written that again here. Rho dot over rho goes like 1 over tau minus tau naught. Okay, consistent with that behavior I described before. Okay, and in fact, we then designed a potential, which is the thing I actually graphed before. Okay, which tends to 0 at large phi and has a de Sitter minimum. Okay, and we solved the equations for this potential and found the sort of behavior that I described before. Okay, so this is the potential again. This is this model potential. This is phi, for example, as it's oscillating inside this region here, and then passes over the barrier. All right. So so what are the implications of this singularity? Well, the real question is whether the singularity is an obstruction to any sort of systematic analysis. If we have a weak coupling, small curvature description of the system, then allowing a perturbative analysis, we expect to be able to write an effective action, including terms of successively higher dimension. So things like r squared, r to the 4th, and things with higher power, so derivatives. If we have this sort of singularity, if phi dot behaves as 1 over t minus t naught, and r behaves like 1 over t minus t naught squared, the lower order terms in this expansion diverge and the expansion breaks down. And this is similar to the phenomenon I described earlier for behavior of a system on the other side of the barrier, okay, for the obstacles to describing this Big Bang or Big Crunch singularity. Okay, so that's kind of my story here. We've argued sort of from 2 points of view that one can't construct a de Sitter space in any controlled approximation in string theory. First, we've seen that even allowing the possibility of arbitrarily large fluxes, it is very difficult to find stationary points for which both the string coupling is small and the compactification radii are large, even before asking whether the corresponding cosmological constant is positive or negative. Okay, we have seen that typically when sensible stationary points exist, even if formally the radii large and the couplings are small, even if such points exist, higher order terms in the expansion are not small. Okay, but our second obstacle seems even more difficult to surmount. A set of small perturbations of any would-be metastable de Sitter space classically will evolve to uncontrollable singularities. Okay, so what am I trying to conclude from this? Okay, you know, I mean, you could say, well, okay, yeah, we knew it was difficult. Well, I think it's, you know, it's sort of, in a fundamental level, it's difficult. This is not really an argument that metastable de Sitter states do not exist in quantum theories of gravity, but only that they are not accessible. They are sort of a priori not accessible to controlled approximations. Okay, and the problem, as I say, is similar to the problem of Big Bang and Big Crunch singularities. We have sort of string theories for which we expect those, and we don't know how to describe such singularities. Okay, all right. So let me mention a couple other things. My time is just about up. So just a couple other points about this. So one is KKLT, as many of you are surely familiar with, is a construction which purports to provide examples of de Sitter vacua. And in fact, in subsequent to the Uguri-Balfa et al. Work, Kachur and others have tried to address this. I would just say that in some sense, KKLT doesn't really fit into the picture which I've been describing now. The small parameter is something somewhat different. So there one imagines one has actually some vast set of states, and sort of at random there's some number with some controlled approximation. And you can't pull that out of your hat. You can't find that particular state. The arguments are basically statistical. So KITP is in a somewhat different category and is an example of something which, again, indicates to the extent to which, to some extent, all this is existence or not, is conjectural. Such states, if they exist, would still be subject to this instability, which I've described before. And there's another aspect of all this which certainly interests me and troubles me, considering the cosmic landscape. The lack of weak coupling suggests that long-lived de Sitter vacuum will be rare. Okay, and we actually heard some issues related to that in John Marshall Russell's talk. But one instance which this is of course an issue is the state which we currently inhabit. Okay, so if weak coupling is rare, we might expect stability is rare, and we'd have to be lucky unless we are to understand why why we live in a state which survives as long as it does. And I might wake up in a cold sweat if the arguments are, for example, I wanted to invoke we're anthropic, that would be fine. But I don't know if I got an anthropic argument why I have to be alive tomorrow if I'm not alive today. Joe Polchinski used to talk about the Joe principle. And I think that certainly comes to mind in this context. One framework which might explain stability is some degree of approximate supersymmetry. If supersymmetry, if you have some approximate supersymmetry, one can understand rather automatically why and we have small cosmological constant, why our vacuum is long-lived. That, of course, raises issues, again, related to some of John's remarks this morning. Again, such states are likely not weakly coupled, and finding them would be challenging. So I think, so again, I think ultimately at a quantum level, reliably establishing the existence of metastable de Sitter states looks like a very challenging problem. One needs a cosmic history necessary to understand this history that this history be under theoretical control, both in the past and in the future. And as a result, the failure to find stationary points of an effective action describing metastable de Sitter space is not clear. Okay, and so I think there I'll conclude. I'm sorry, I've gone a couple minutes over. But I thank you for your attention and look forward to any comments.
All right, thanks very much, Michael, for that very stimulating talk. I'm sure there will be follow-up questions to this. If anyone has them, please either raise your hand or just go ahead and unmute and ask.
Michael, if I may, this is Tom Banks.
Yeah, good to hear you, Tom.
Yeah, nice talk, thank you. I have two sort of related questions. There's a whole history of papers that talk about things that sometimes go under the name of the no-hair theorem for de Sitter space. Those would seem to be in contradiction with what you were saying about an arbitrary de Sitter space of this type will have small perturbations that destabilize it. And the other question that's related to that I want to ask is that the Stanford group had this whole story in which they took the Coleman de Lucia instanton for the decay of de Sitter space into a flat space. And they sort of tried to cook up a kind of scattering theory that would give you a prehistory for de Sitter cosmology and then a stable evolution out of that. And you seem to be saying that doesn't work either. And I'm not sure I understand technically where you're differing from that.
Well, I'm not sure I'm going to give you, I might throw the questions back at you. These are good questions. I think for the second part, I think I only have a vague answer, which is that if we live, if the underlying, so first of all, I'm you've thought harder than I about the question of what the underlying theory might be. It's not it's not really, we don't think that string theory is exactly a quantum field theory generalized in some way, for example. But thinking of it sort of by analogy to quantum field theory, I'm sort of imagining that we have some kind of space with a potential which has lots of wiggles in it. The wiggles are not very large. The wells are not deep, and we don't get stuck largely. So we'll only get stuck occasionally. So I'm not sure how to. I don't have a. So for example, in the kind of picture that one often thinks about for landscape evolution, I don't have a clear idea. I don't. The idea that you sort of get someplace, you tunnel to another, things like that don't seem like the correct way of thinking about it. I don't think I've got a better answer to that. And to your argument, I'd be curious to understand that better. I say I don't quite. I don't know whether that might depend, for example, on this question of the asymptotic behavior of the potential, which is obviously critical for this.
I think I can say something about that.
Thank you, Gary.
Yes.
Gary?
Yes. So, I mean, your arguments for instability were classical. Yeah, this is Gary Horowitz. And it reminds me of, old arguments. If you take gravity coupled to a homogeneous scalar field, and you go back very early in time to the, your universe is very large and collapsing, it's known that all you have to do is add a very small amount of energy to the scalar field, and it gets blue shifted when the universe is in a collapsing phase. And if that initial energy is bigger than a small critical amount, the universe won't bounce and will simply collapse to a big crunch. And
it does feel similar to this, yeah.
Yeah, so it's similar to what you're saying, and it's known that if you perturb an earlier time slice, the critical amount you need gets smaller, because you have more time for a blue shift to take effect, and the energy just is building up and stuff. But we still say de Sitter is stable, and Tom is right. There are theorems which say that if you take initial data, there is an open set. You can consider sufficiently small perturbation so that it does bounce and you end up asymptotically de Sitter. So I think the difference is you were talking about perturbations causing, singularities, but your perturbations could not be arbitrarily small. You needed them bigger than a critical amount in order to cause the instability. And so if you take your perturbations arbitrarily small, then everything will be fine. You don't have an instability. So it's a question of, do you have an estimate of how big your perturbations are expected to be for some reason? But I don't think, so the difference is you need finite perturbations bigger than a certain amount, and not arbitrarily small perturbations.
I think what I have in mind here, I agree, I totally agree. So there's some, if I think about this parameter that appeared in the de Sitter metric, this tau, as I take tau to be larger and more negative, then I need my perturbations to be smaller. I think the question, so I think this question has to do with how, you probably know more about, you surely know more about this than me. There's a literature on, whether or not one can construct S matrices in de Sitter space and so on. In string theory, we're used to the idea that what sort of defines a critical string theory. What defines a critical string theory is, a statement about, the existence of a sensible S matrix. And I tried to sort of say that that's something like the statement classically that small disturbances propagate sensibly. And what I'm probably lacking, and I think what your comment illustrates, is a sharp statement about what that limitation is. So I was really mainly trying to argue that in string theory, I don't know what the question is. That you to say what when we say we're seeking, what are we looking for? And that probably could be sharpened up in some way. And perhaps you or Tom may have some ideas about how one might do that. but it might well be there's a statement about if, maybe a counter to what I say is if the perturbations are small enough, it's okay. And with the definition of small enough, I don't know what it is, but maybe there is such a thing.
Well, I think if you're thinking about scattering, you're setting in a few particles, and so an energy density is certainly is zero, basically, if the universe is getting arbitrarily big at early times. So
Right.
certainly not a finite energy density.
Yeah. That was a good question. So I don't have, so the answer is I don't have a real sharp answer to these questions.
Other questions, comments?
Michael, can I ask a question? John.
Of course.
Please go ahead.
I'm a little bit confused about your comment about KLT. It doesn't seem to matter of principle there's such a big difference between that and just the large flux. Because if we accept that the topological complexity of compactations is not arbitrarily big, there is some limitation, which seems to be reasonably accepted, and we accept that we can't put arbitrary flux quanta in a given particular cycle. In fact, we can't tune W0 arbitrarily small, so we can't take it completely. There's always a sort of a lower critical threshold for that step size. So isn't it again true we don't have a parameter we can truly take to zero and expand?
Yeah, that's really what I think that's what I had in mind, actually. We don't have such a parameter.
Yes.
So we don't have. So there are two issues. One is we don't really have a parameter we can take arbitrarily small. And the other is that we don't really have, in general, if you just construct some random point in that space, W0, the parameter, which is this small parameter for the theory, will not be particularly small.
Yes.
So you don't really, unless you have an unimaginably powerful computer or something, you can survey some large number, you're not going to get to do this. So that's all I really was referring to. That this is a kind of different kettle of fish, and that only there's some kind of speculation involved in whether or not you believe such things exist. And I'm quite comfortable with speculating that they exist. In some sense, I'm pushing back a little bit against the Swampland conjecture. But I'm also, if you tell me no, I also, if you're Safsethi or, various, I say, okay, sure, I have no argument. I don't really have an argument one way or the other.
Okay, thank you.
Does your picture of instabilities from perturbations give you some constraints on getting stuck in a false vacuum as you cool? My picture for this is forming, getting stuck there because the early universe is very hot.
I'm not sure. It perhaps gets to the previous talk a little bit too.
Yeah.
Hi, Michael. This is Yasunori.
Yeah.
Hey, so about these two things about KKLT and a large flux, it's just simply like something like a fixed point of the RGE. You can make it coupling to be strong, and one loop and two loop piece bounces with each other in the strong coupling. Then you can't control the approximation because 3 loop is the same order, 4 loop is the same order. But the other is a bank stacks, right? I mean, you can tune color and flavor and accidentally small, and then one loop balance with the two loop without going to strong coupling, and that's just the KKLT, right? And
I guess the question, I'm not sure if I understand. The question I was thinking of sort of John's question about KKLT has various features.
Yeah.
And one of which that's important is this parameter W0, the expectation value of some superpotential due to some subset of the moduli.
But I'm saying that if you do prepare a small number by accident in one place, then you can do controlled, it's literally like bank stacks fixed point. Like you do the accidental separation of the one loop piece by near cancellation of integer numbers, colors, and the flavors. Then you don't need to go to strong coupling to balance a one loop piece and two loop piece. And then you just lose the control, of course. If I go to G equal 4 pi, then you lose it. But then that's the way to do by large flux, and you balance it, then you lose everything. But you usually usually you can have a small parameter space, and that's happening even in QFT, in bank stats and so on. So pretty natural that this KKLT thing is happening. That's one thing. The second thing is that this dositor, like initial condition, if you prepare dositor as a kind of metastable bound state from Minkowski scattering in some sense, okay, non-perturbative scattering, then you have to fine tune initial condition exponentially anyway. This is something like forming a bound state from some two particles. Then of course your momentum and so must be pretty, fine-tuned to get the two particles to the bound state. So you really exponentially fine-tuning the dositor space anyway. So your initial perturbation need not be beyond the critical size you assume. I mean, we anyway allowing kind of dositor is a finite entropy system, and Minkowski is infinite entropy system. So you must allow infinite fine-tuning anyway in some sense from a generic microscopic state point of view. So I don't see any reason why this perturbation has to be bigger than critical as you kind of assuming here.
Okay. Well, I'll have to think about this a little bit. I'm not sure I'm fully, maybe Gary has some comments. I'm not sure I fully understand. But I think, I do think these comments of Tom's and Gary's certainly give me something to think about in terms of what are the perturbations that we're allowing? Are there some restrictions?
Yeah, I'm certainly not saying that it's likely that, but at least I don't see reason why it has to be as big as you thought. I mean.
Okay.
Yeah, that's it. Yeah, that was a question. Yeah.
Good. Let's see. There was a question from Davud. I don't know if that got answered.
Oh, in the Slack channel. Sure.
In the Slack channel or in the chat. I'm actually looking mostly at the chat, I'm afraid.
Oh, okay.
I'm not sure. Let's see. Non-linear ODE. Anyway, perhaps before as I look for that, if there are any other questions, but I appreciate the questions that from all of you.
I would like to make a comment.
Please.
First of all, thanks for the talk. Regarding the question of small w naught, maybe I misunderstood, but I thought what you said is that the problem with it is that it's hard to imagine and to find explicitly such small w naught vacuum to actually have a systematic scheme of computation. I just wanted to point out that in December I had a paper with Liam McAllister, Menki Kim, and Mehmet Demetis, where we actually showed how you can find such vacuum with very small w naught explicit.
Very small. Sorry, I couldn't hear you.
We did find a way to find explicit vacuum with extremely small, so exponentially small superpotentials explicitly. So, for instance, with little computation, so with almost no computational effort, you can find vacuum with like 10 to the minus 8. So this is possible to do.
Okay, this is a sort of a KLT variant, or?
Yes, it's basically a way to find small W naught in the standard flux landscape of type 2B.
Okay, okay. Apologize, I'm not aware of that. That sounds very. In terms of notes from the various talks and things I've learned this morning, that's important. I will take a look at that. Perhaps by the time we meet tomorrow, I will have had a chance to think about it a little bit. Thank you.
Sure.
Okay, so we've reached sort of the end of our session here, and we'll pick up again tomorrow at the same time. Thanks to all of the speakers that spoke today. Really appreciate your talks, and for everyone who participated.